Okay, here's a video that illustrates successive approximation for analog to digital conversion. Remember, we talked in class about how algorithms can be used to design hardware, and here's an algorithm that implements successive approximation. Okay, the thing to notice in the algorithm is that you're going to need a parameter q, all right? And we talked about this before. This is the quantization levels. Each of those are spaced apart by q. And so the way we would find q is we'd take the range of the quantizer and divide by the number of levels. Since this is a 4-bit quantizer, then this would be 16 levels, and you get a q value of 0.625. All right, this particular algorithm adds a q over 2 to help with round off. All right, one of the other things you need to notice whenever you come up with some type of successive approximation algorithm, you need to decide on what is the code that's going to be used to represent each output. All right, that's essentially done by defining how you do the opposite process of digital to analog conversion. So if you think about that, what that means is you take a sequence of bits, all right, come up with some formula or scheme to determine what the output, the analog output would be for those sequence of that particular sequence of bits. Okay, so in this case, what we're going to use is 2's complement. Okay, so here's the formula for 2's complement. All right, you talked about this way back in digital logic. Once we know the bit pattern, we can plug in the bits and calculate xq. All right, another thing to notice from the formula is that the very first bit is set according to the sign of the number. All right, so you calculate y is equal to x plus q over 2, which we did here. You get 3.8125. Since that's a positive number, then you remember from 2's complement, if it's a positive number, you set the most significant bit to 0. Okay, so as we go through this algorithm, we know immediately the first bit is a 0 for quantizing x equal 3.5. All right, so then we go to the next step, which would be I is equal to 2. All right, so we're starting off with the second bit. We would flip that bit on and leave all the others off. All right, when you do that, that's what this means. Flip this on, leave all the others off by default. The next thing you need to do is calculate xq. All right, so let's do that in detail for the first one. All right, so xq is going to be r, which is 10, and then we take b1 complement. All right, so that would be a 1 times 2 to the minus 1, which would be a half. All right, plus b2 is also turned on, so that's 1/4. All the others are off, and then we subtract off 1/2. That's according to the formula. All right, so these cancel, and what we get for the first step in this process is xq is 2.5. All right, so from there we look at xq and we determine should we leave that bit on or not. Okay, so I have a little flow chart for you. Okay, so xq is 2.5. All right, is y greater than 2.5? If it's yes, in this case it is. I got these reversed. Okay, so let's flip that. Sorry, this should be no, and this should be yes. Okay, if y is less than or greater than q over a, we keep that bit set. If it's not, we would clear it. All right, since it is, we keep it, and we move on to the next in value. All right, so the next bit value would be bit 3. All right, so for that step, we now set that to a 1. Okay, when we set that to a 1, that changes XQ. XQ would now be 3.75. Okay, so we do the same type of comparison with 3.75. 3.8125 is bigger than 3.75, so we keep that bit as well. All right. All right, so I'm going to mark the ones that we keep in green. All right, that one's easy. We just set it with the sign bit. We keep this one, and we keep this one. All right, so let's go to the next stage. Okay, so for the next stage, we would set the B4 bit. Okay, when I set the B4 bit, that turns these on. When you plug that into the XQ formula, you get, I'm sorry, I got the wrong line here. When you set those to 0, 1, 0, 1, 1, 1, you produce an output of 4.375. The next step in the algorithm is 4.375 greater than 3.8125? It is not. Okay, and so we would clear that particular bit. Okay, so this one gets set back to a 0. We can mark that in a different color, say red. Okay, so at that point you stop. All right, this would be flipped back, and the final answer is 0, 1, 1, 0 for quantizing the number 3.5.